Okay, so sorry for people who are watching this recording. I just remembered to start the recording. So we're partway through the solution. All right, so we're looking at this free body diagram. All right, so here I've put in the direction of the force that's going to be acting at D. So we can just guess the sense, or you can have a look at these forces down here and work out whether the sense is going to be up to the right or down to the left. Doesn't matter if you get it wrong. If you had it going down to the left, then it will just come out negative. Give it a label, and then because I'm thinking ahead to what I'm going to be doing, I know that I'm going to need this angle in here, so I've just calculated that. Okay, the first time I did this problem, I actually got this angle wrong. I had in here, I just did a 120 plus 290 equals 310 instead of 410. Right? If that kind of things happens to you in your quiz and you're a long way through the solution, don't go back and try and change everything. Just indicate somewhere, oh, look, I've put in here 310 instead of 410. So the rest of my calculations will be out slightly because of this. And if you do that, then I'm going to mark the rest of the thing correct. Anyway, so this should be right now. So if you go back and look at your diagram, you can see that. So back up here. So here's 60, and this length here is 120 plus 290. Okay, and then at A, it's just a pin connection. So horizontal and vertical reaction force components. Again, you can just try and guess, or you can just put on the arrowheads for the sense, or you can have a look at the problem and try and work it out. That's what I thought they might be. Could be wrong. Find out. And then label your forces with sensible labels. Is this A supposed to be C? It is, yes. Thank you. Why did I do that? What's easier to change? I think the question might be easier to change. Let me change the question. Thanks for that, Roy. Thanks for picking that up. Okay, so once we get to this point in the solution, it's now just an intro to mech quiz 2 problem. Right? Just a simple rigid body equilibrium problem. Okay. So if we do sum of the moments about A equals 0. Why did I choose A? So I can find RD straight away. If I chose to take moments about point D, which is not wrong. So I think there was a question before, someone chose said they chose the wrong point to take moments about. All that does is just make it take a little bit longer to do your solution. Right? It won't cause you to get, well, assuming you do all of your algebra correctly, it won't cause you to have a wrong solution. Yeah, so if you did moments about D, then we would have 2 unknowns here. And then we just got to do a bit more algebra to find the unknowns. All right, so we can work our way through that. So we'll have 1.5 times 0.16 going anti-clockwise about point A, so that's positive. I think this part probably should be okay for most people, so I'm going to go through pretty quickly with this just to give us a bit of time. And just stop and let you absorb what I've written there, and then I'll allow you to ask some questions. -2. Okay, thanks, Alex. So if you look here, that's big. Yeah, the other problem when I was doing these solutions is that it crashed in the middle of me fixing it up, and it should be 1. So that will probably mean that some of my numbers are wrong down here, because I've missed that one when I was fixing it up after it crashed. Note how easy it is to find my mistakes. Right?
Terry,
Yes.
you know for oh, never mind. Sorry, I didn't read it properly. I was gonna say because one of the mistakes I made was I didn't put a minus moment for, you know how you did -1 times
Yeah.
0.18. Yeah, I didn't. I didn't imagine the thing properly and thought it was and wrote it as positive.
Yeah.
But yeah, that was one of the mistakes that I made as well.
Yeah.
But
yeah, that can happen.
yeah, that's what I realized at the end as well.
Yeah. Yeah, and again, you know, in a quiz, and if you run out of, or even in an assignment, you know, don't redo the whole thing. Just put a note here and say, oh, I realised after I went back and checked through my working that this minus should have been a plus, or this plus should have been a minus. So therefore, my numbers are going to be wrong, but my methods and working out should be correct.
Okay.
Same as in mine, you know, what happened here with the 2 is instead of looking over here properly, I still had in my mind that the variation, so the odd or the even, whichever one I'm not doing, had 2 here. Or when I was creating, I think when I was creating the question, I originally had 2, and then I just changed my mind and made it 1. Where did I get the 0.3 from? Hopefully I haven't made another mistake. So let's just go back. So RD. So here we're taking moments about, yeah, so thanks Seti. Yeah. So taking moments about point A. So it's 480 minus 180. So rearrange that. So you can see here, I fixed it here. Right? The one where I had the 1. Where I had 2 up here, right? I've actually got 1 in here, so I fixed it up. Just missed that up there. So hopefully the numbers are right now. So that's just algebra. We don't need to talk about that very much. So I've got a number, and then some of the forces. I don't think I need to talk about this very much. I think this is the easy part, hopefully. But I will just leave that there just for a little bit, and just in case anyone's got questions.
I can really see already how much it changes if you do sort of pick the correct moment at the start, like how quick you can get an answer.
Yeah.
Compared to like the way I did it, for sure.
Yeah.
Yeah. So would you say in the future it's sort of best bet to try to go for couples first? In questions like this, or does it really depend on the question?
When you have a rigid body equilibrium problem, nearly always, 90% or more of the time, the best thing to do is to take moments about the point where your 2 unknown reactions are.
Yeah.
So mostly you'll have either a pin connection and a roller, or a smooth contact, or connection to a 2-force member. So at one of the locations where you have unknowns, you'll know a direction. And then at the other location, you'll have 2 components like this.
Yeah.
So nearly always, the best thing to do is to take moments about the point where you've got these 2 unknowns.
Yeah, I see what you're saying.
Yeah. Because that way you can find this RD can be found straight away.
Yeah, I made 2 mistakes in my one. The first one was an algebra mistake.
Yeah.
And then, because I realized it was algebra mistake because my RAY was like too big, I think it was. It didn't make any sense.
Yeah.
And then I went back and I realized the algebra mistake. But then figured out the moment mistake as well after the algebra mistake.
Yeah.
And then, yeah, I have the same answers as that as well. So, but then it was too late, of course.
Yeah. So yeah, that was for me the biggest problem was the lack of time. But if you really knew what you're doing, there was still lack of time if you knew what you were doing. For a lot of people, I think wouldn't have mattered how much time you had. You wouldn't have got to the right answer because you just started completely wrongly. Yeah. So and if you I think Isaac has put in the chat there. You didn't realise that you could draw this one thing as a free body diagram. That's why I put in here. Right? Treat the wheel and upright as a single rigid body. That's because I anticipated that. So I put in this information here so that hopefully you would realise that you could just treat all of this as one rigid body. Maybe if I didn't have this vertical line here, that might have helped. Anyway, what's done is done.
Yeah, so the intuition is pretty important because even though I made 2 mistakes because of the fact that the forces were clearly not like correct, because they were bigger than the actual counter forces or whatever, you could tell that it was wrong. So
what do you mean by intuition though?
Because well, not intuition, I guess just understanding that.
That's better, right?
Yeah, that's a better word. Yeah.
Yeah. So you shouldn't need, in my opinion, you shouldn't need intuition to solve this problem, right? You should be able to solve this problem by disciplined application of the basics.
Yeah.
Right?
Yeah, I guess, yeah. So understanding that the forces were too big and going back and seeing that the mistakes, detecting the mistakes.
Yeah.
Terry,
yes.
I have a question. If you didn't write a hint there to treat this upright thing as one rigid body, and how are we supposed to identify like where we can identify a single rigid body? Like for this question, we have to separate this structure into 2 rigid structures, and this is one of them you're showing, and the other one should be ABC, I believe.
Yeah.
And if without your hint, how are we supposed to identify that?
Well, where are we? So if we go back to this one.
Yeah.
Right. So this one is just ABC. You should be able to just look at that and say that's just one body. I don't think I need to tell you that's just one body.
Yeah, but when we do a question, that is we can treat that as a single body because of like it's joined at A with a pin or something.
Yeah.
Okay. So if something is one structure is joined with another structure with a pin connection, then we can treat these 2. We can treat this structure as 2 separate structures.
Yeah, absolutely. Yeah.
Okay.
Yeah. So if they're pin connected, you have to do that to solve the problem.
Okay.
Right. You have to be able to disassemble. You have to be able to imagine that you've disassembled the assembly of structural components.
Yeah.
Right. And when you're drawing your free body diagram, so if we go to our next page, right? When we draw our free body diagram here, when we draw these forces here, what these forces represent are the interaction between this body and the body that we've moved, right? So that lower body ABC, right, exerts RAX and RAY on this upright.
Okay.
Okay. And then when we go to the next page and draw the free body diagram of ABC, we'll have equal and opposite at A.
Yeah.
Right? Because what we'll be showing on that lower member are the forces that the upright exerts on the lower control arm.
Mm-hmm.
Yeah.
Okay. So what if I assume the direction of the RAX and RAY incorrectly in here, and also RD? It shouldn't play any major role, right? We just get a negative number, and we know the force should be in the other direction.
Correct.
Okay, sure. Because I found that more than half of the time, I always assume the direction of the force wrong.
Yeah. Well, in fact, I think I get it wrong in. I think I've got RAX wrong from memory in my solution.
Okay, but you didn't get a negative number here.
Okay, might be in the next one.
Okay, sure. Until we go to the next. Thanks, Terry.
Yeah. Sometimes when I'm doing these problems for teaching, I do it on purpose, right? Even though I know the right sense of the force, I'll put it on my diagram incorrectly just to show what happens if you get it wrong.
Yeah, I think you should do that because we can't, like, when we do a question, we can't always assume the force is correct. You can't always assume the right thing.
Yeah. So if it's not in this one, it's in the example that I'm doing later.
Okay. Thanks, Terry.
Yeah. Let's see. All right. So now onto the lower control arm. Just have a think. Why did I choose to draw a free body diagram of this thing? Let's go back to the question. Right. So we've now got the force here at E, and we've got the force here at A, or forces at A, and we're wanting to find the forces in all of these locations. Right. So D, right, or E, we know we've already got because it's a two force member. It's just be equal and opposite to force D here that we've already found. So we don't need to draw a free body diagram of that. Right. Also, that's the other thing. I noticed a lot of people drew free body diagrams of the two force members. It's not wrong to do that, but you didn't really need to do that. I often do it when I'm teaching, just to try and explain and help you to understand about the two force members. But you know, in your solution to the quiz, you didn't really need to draw that. All right, so then we've got, you're wanting to know the forces at B and C. So if you find B, BF is a two force member. So if you find B, we've got F. So the only other thing we need is C. So the logical thing, if you think through it, to draw a free body diagram of is this lower control arm. Okay, so start with that. So then at A, as I said, we know we've got a pin connection here. So we're now going to have a vertical and horizontal force. But when we draw the sense of these ones, we need to refer back to our other free body diagram. Right? We need to refer back to here and make sure that we put the opposite sense on the connecting free body. Yep. So here we've got to the right and down. So on the other member, we'll need to have to the left and up. I haven't put that on yet. Before we get to that, BF is a two force member, so we know its direction. At C, we've got a pin connection. Don't know the sense of those. So what did I say? We needed to be up to the left. So you can see that these are opposite to what we had over here. Opposite to these. To work out the sense of this force here, just imagine that you're taking moments about point C. This force is going to tend to rotate this anti-clockwise, right, about point C. So force at B must be acting downwards to the right. Now I've just carried this stuff over from the previous page. Right, so here you can again look at your free body diagram and try and work out the sense of these things, or you can just put whatever you like. If you're not sure, just put them in the positive directions. Okay, so I've assumed that. and given them some labels. Okay, so once we get to here, once again, it's simple rigid body equilibrium problem. We've got RA and RAY and RAX that we got from our previous page, previous free body diagram, and now we've just got 3 unknowns again. Just use our 3 equilibrium equations. Which one do we start with? Moments about C, right? Because we've got 2 forces, 2 unknown forces acting through C, so we can take moments about, C and find RB directly. In this case, we could actually take moments about point B, right? And solve straight away for RCY. Right? Because RCX passes through point B. Right? So we could take moments about point B in this case and get RCY straight away. He-Chan has written, but then we calculate using M. Yes, okay, so once we do the algebra, and we get a negative for these things. Yeah, okay, look, don't spend a lot of time on it, okay? If you feel like, so I'm just answering He-Chan's question there about struggling with choosing the direction of the forces. Have a quick think about it because it helps you to think about how you might solve the problem. But, you know, if you can't work it out in 30 to 60 seconds, just put them in the positive directions and see what happens. So we need to do some trigonometry. All right, so I've just taken moments about C as we suggested. So I'm just going to quickly put that up so we can have a look at what we got. So this is a much simpler one, much simpler geometry. Okay, I'm not sure what you're saying there, He-Chan, but let's get to the next bit and you can have a look at what happened with mine and you can and if anyone's got questions about the other bit, you can please type them in or yell them out. So once we've found RB, we can then go to our 2 force equilibrium equations and do those. All right, so here, I thought one of them came out negative. All right, so here, when I chose to the right for RCX, I actually got that wrong. All right, so when I do, so I just apply my equation of equilibrium as per my free body diagram, put it into my equation, right, as per the free body diagram, do my algebra, hopefully correctly, and get a negative value for RCX, which indicates that I chose the wrong sense for RCX. As I said before, so He-Chan's against it. So we always proceed with moment first. As I said before, 90% of the time, yes. You know, you don't have to. You can write the force equation first if you want to, but you'll just you know, so if you had written this equation here first, then we would have had 2 unknowns. Someone's asked, should it be 350 over 180? Could be. Let's just check. So, okay, so He-Chan's right now. So let me just check that geometry and make sure that I haven't stuffed up something. So we want 350. Yes, sorry, that should have been 350. Yeah, so Alex, thanks for picking that up. So yes, that should have been 350, not 360. All right, so that'll obviously change this a little bit. So are you referring to these forces here at A, I assume? Okay, so yeah. Yeah, so whenever you have, and it was the same in all of those tutorial and example quiz problems that we did. Exactly the same thing, right? Whenever you've got 2 bodies that are connected together, when you've got 2 bodies connected together like this, right? and you imagine you separate them in your free body diagram, right? On, let's say you draw the free body diagram of this one, you've got, because there's some forces up here, right? And this here is reacting against them, right? So you'll have reaction force, let's say X and Y on here, okay? So what you draw on this one are the forces that this one exerts on my right hand, okay? And then when you draw a free body diagram of this one, you show what this body is exerting on this body, right? So we started from here, we started from this free body because this is where our loads were, right? So we can't calculate anything anywhere else, right? We've got to have some input values to start doing some calculations. So these forces here enable us to calculate these reaction forces that are generated by this thing being pin connected to something else. Now that something else could be just a pin connection that's connected to ground, like you would have done in the simple one body equilibrium problems, or it could be pin connected to some other body or some other structural member. Okay, so here it's connected to some other structural member by a pin. Okay, so on our next page, here, these forces here are equal and opposite to what was on the previous free body diagram. Because what we're showing here now is the forces that the upright, so the other free body diagram, the forces that the upright are exerted on this body.
Kerry, what would you do if there was a situation like I was just going over the truss stuff before. Yep. If you had a pin that had 3 different structures coming off it, let's say,
yeah,
if you've used 2 to do the equal and opposite, what do you do for the third? I'm not sure if that situation ever actually comes up, but I'm just curious.
It does. It comes up in the problem that I nearly gave you for the quiz.
Oh, that's good.
Right. So if you go into the tutorial problems, which week is it? With this one. Right. So I nearly gave you that as a quiz problem. And here you've got 2 members connected at this point here. I don't know whether you can imagine what the free body diagram is going to look like here. It is, but you know, BD is a 2-force member, BHF is a 2-force member. Right? So
it doesn't really matter then because it's not really the X and Y components.
So let's see what they've got in their solution here. No, they don't have a free body diagram of this bottom bit. Right, so if you did draw the free body diagram of these 2 members, right, you'd have equal and opposite. Let me see if I can do this. Sorry, this is really hard to. All right, so there's the bottom member ABC, and that's B. If we have our 2-force member here, like this, then, so that will be exerting a force on here at B.
Yeah.
This lower member here, ABC, will be exerting equal and opposite here.
Yeah, I get that because couple.
Yeah.
I mean, not couple. Sorry.
2-force member.
Yeah, 2-force member. Yeah.
If it wasn't, let's say there was another force acting on here, then the same thing applies. So you could just you just got to still follow your process. If it's not a 3-force member, then you just have to go, okay, well, this is like that, and then on here you'd have the opposite. Whoops, wrong way.
But let's say like hypothetically, if BD wasn't a 2 force member as well, is there a situation where, because you can't really have 3 that are equal and opposite, can you? Do you sort of get what I'm saying? Or
Yeah.
not?
It would be it becomes a difficult problem, but you still got to follow this same process. So,
Okay.
if BD was also not a 2 force member, then you'd have to do the same thing, right? So you've got this other one here, and you just have to add them all up somehow, right? So what you would, so that's a bit of a bad BD, but let's say there was a force acting on the middle of this thing. Right? So then you've got a reaction force here, and then another at the other end, you've got the same thing. So it's probably going to be statically indeterminate and you can't solve it.
Oh, okay. Yeah, I remember that from, I think it was last week.
Yeah, right.
Yeah.
So you may just end up with too many unknowns.
Yeah. And that's a different subject. You learn that stuff out.
Yeah.
Isn't it? Yeah.
Yeah.
Okay, cool. Thank you for clearing that up. I was just curious.
Yeah, no, that's good. Thanks.
When
right.
you say it's unsolvable, still probably something.
You're talking to me. If you're not talking to me, mute your microphone.
I was talking to you, sorry. Could you not hear me? Can you hear me?
Yeah, sorry.
When you say it's not solvable, would it really still be solvable with like a computer or using matrices? Or is it really actually not solvable?
If it's statically indeterminate, if it's what we call statically indeterminate, you end up with too many unknowns. Okay, so you might end up with 4 unknowns. So if you had this problem here, right, if BD really was this, and it was pin connected at both ends, then you've got 1, 2, 3, 4 unknowns, and only 3 equations of equilibrium to solve for it. Okay, doesn't matter what computer you use, you're not going to be able to solve.
Yeah, I get you.
You just don't have enough information, enough equations.
Yeah,
right?
yeah.
So what we do is in Mech Solids, I think, definitely strength of engineering materials, you start to look at the deformation of the members. Okay, and so you say, all right, this point here, D is connected and not going anywhere. So I look, okay, so this will deform a certain amount, but we've got a reaction force that pushes it back. So the action, then we use what we call superposition. Getting beyond this subject, but so we need more information to enable us to have another equation that we can use to solve for our unknown. Right? The other way is, if you did a computer model of this and use finite element analysis to solve it, you could do it that way, and that's essentially using the computer to do what I was just talking about, looking at the deflections of the members and the relative stiffnesses of things to work out how the load is shared amongst these over-constrained reaction forces.
Interesting. Thank you.